In this section, we are going to review resistors in series. This should be a pretty straightforward section for us because you have seen this in your physics and your prerequisite courses and your high school classes. Simply, the formal definition of series connection is when only two elements are connected to a node at a single point, they are said to be in series. Okay, the two resistances R1 and R2, right, they are in series because they are connected at a single node, and then there is nothing else connected to that node. Okay, so R1 and R2 are in series, and so are R2 and R3. Okay, as a matter of fact, all the 7 resistances that you see, R1, R2, R3, R4, R5, R6 and 7, these are all in series. Okay, the fundamental defining characteristic of series is that all series elements have the same current. Okay, so for example, for the current that is being supplied by the voltage source, whatever current enters into R1 has nowhere else but to enter R2. Okay, so the current I1 that is flowing through R1 is the same as the current I2 that is flowing to R2, and the current I3 that is flowing through R3, and so on. Okay, so if you have one straight road, all the traffic that is entering the road has nowhere else to go. Okay, if there were a parallel path here, then the cars coming in this road could branch into two different paths, but that's not the case, right? So since they are series connected, all the elements here, all the resistors here have the same current. Okay, so the current I1 that is flowing through R1 is the same as the current I2 that is flowing through R2, okay, I1, and so on and so forth. I3, that's the current flowing through R3. They're all the same and they're equal to the I source. Okay, so simply we are going to refer to the current in this series element, in this series circuit as IS, I series current supplied by the source, right? But what is different though is the voltage that is set up, the voltage that is dropped across each of these resistances. That's different. V1 is different from V2, which is different from V3. Okay, so each of these resistances have separate, different values, V5, V6, and V7. So the voltage is dropped in each of these resistances, across each of these resistances. That is different. Okay, so you will see that when you look at this guy, okay, when you look at this series connection of resistors, you're going to see that this is simply equivalent to one voltage source connected to one resistance R equivalent. Okay, they behave, both of these circuits behave exactly the same. Okay, the equivalent circuit on the right and the series connection on the left, they're both the same. They behave exactly the same with respect to these green terminals. Okay, so the amount of current and the voltage set up across these terminals, they're the same between these two circuits. Okay, and I'm going to show you that R equivalent, when you have a bunch of resistors in series, simply the equivalent resistance is the sum of all those resistances. There are a bunch of these resistances, R7. Okay, if you have n resistances in series, then the equivalent resistance is going to be the sum of all the resistances from 1 to n, if there are n resistances in series. Okay, so that is the equivalent resistance in series. Now we can get this result. I'm kind of giving you the result up front. We can get this result. How did I get this result? It's pretty straightforward. If we use KVL, Kirchhoff's voltage law, around this loop, okay, so you choose a closed path. That's the closed path I'm choosing, okay, and apply Kirchhoff's voltage law around that closed path. Then you can arrive at this result. Okay, so let me show that to you. Let me demonstrate how I arrived at this result. R equivalent is equal to sum of the resistances. That's pretty simple to show actually. So let's do the KVL. Okay, so let's apply the KVL. We start at the bottom left and go around the loop and add up all the voltages. Okay, so starting at the bottom of the loop and going through this loop, we encounter negative terminal and positive terminal Vs. Okay, so Vs starting with a negative terminal. So that says negative Vs, right? Then I go to the next element where I see plus minus V1, right? So I'm going to add the voltage drop with a plus V1 sign. Okay, the next element that I encounter is R2, where the voltage drop is plus minus V2. So we are going along the loop, along the green path, right, and adding up the voltage drops. So along this green path, we are adding up the voltage drops. Now we are at R2, where the voltage is plus or minus V2, so we add that. The same for the third resistance as well. The resistance here, you see there is a plus and there is a minus V3. Okay, so we add that in plus minus format. Okay, so we start with the plus and then minus, so plus V3. So as you go around the loop, you will see that all the voltages have a plus sign associated with them. And now you have completed the loop along the green path, V1, V2, V3, 4, 5, 6, and 7. Once you accounted for all the voltages, including the source voltage, and V1, and all the way up to V7, then you have completely added all the voltages, okay, in the closed loop. Now what KVL says, and that's the definition of KVL, right? KVL says that all of these voltages sum to 0. Okay, so in other words, the sum of all these voltages, V1 plus V2 plus V3, that is equals to, take this to the other side of the equation, you will end up with Vs on the other side, positive Vs. Okay, plus Vs. You'll see that all of these voltages add up to Vs. Now if you think about it, this guy V1, what is V1? That's the voltage dropped across resistance R1, right? Voltage dropped across resistance R1. But we know from Ohm's law that it is Is times R1 because it has a current of Is and a resistance of R1. So V2 similarly has a current of Is and a resistance of R2. So the voltage dropped across V2 is Is times R2, so on and so on. Okay, so if I plug that in, let's see what happens. So V1, I'm going to write it as Is times R1 using Ohm's law plus Is times R2 plus Is times R3, that is for V3, and then V4 is really Is R4 plus all of that equals to Vs, right? So factor out Is, I have the sum of these resistances R1 plus R2 plus R6 plus R7, all of that equals to Vs. Okay, so the idea is if I had one equivalent circuit, one current, one voltage source, okay, let's see if I had a voltage source Vs that is connected to a resistance R equivalent, okay. For this circuit, okay, for all of this circuit to be equivalent to the series connection shown here, for these two circuits to be equivalent, we have to see that the voltages and the currents are exactly the same. Okay, that is what makes this two circuits equivalent. Okay, so the voltage, so in other words, the Vs that is set up across the equivalent resistance is Is times R equivalent. Okay, so if you want the Vs to be equivalent from both of these circuits, then it dictates that the currents and the voltage drops this side of the equation will equal that side of the equation. What you will see is that by equating the appropriate left hand side and the right hand side of the equation, we can do that because both of these circuits are equivalent. That's the premise, right? So now you can see that you can factor out Is on both sides. You can cancel Is on both sides. You are left with this expression. R equivalent is R1 plus R2, R3. Let me actually copy this. I'm tired of writing it over and over again. So this is exactly the result we started out by defining, right? If you go back, when a bunch of resistances are connected in series, the equivalent resistance is the sum of the resistances. And we could have stopped there. What we simply did is to look at KVL and see how we can derive that expression. So, in series, sum of resistances is the equivalent resistance.